Okay, let me start it. So, hello everyone. Welcome to this Young Achiever seminar. So, my name is Wang, a second-year PhD student in IST. In this semester, I'm helping the Center for Socially Responsible AI organize this talk series. So today is our final talk in this semester. We are happy to have Serena Wang, a fifth-year PhD student from University of California, Berkeley, to share her research related to AI for social impact. Her research focuses on understanding and improving the long-term societal impacts of machine learning by rethinking machine learning algorithms and their surrounding incentives and practice. So for today's talk, we will have two parts. In the first session, Serena will share her research at first, and then in the second part, we will have a 5 to 10 minutes Q&A session. So shall we start, Serena?
Yes.
Okay.
Okay, let me now fix the share. Okay, are the slides showing up okay? Yeah. Okay, great. Well, thank you so much for inviting me. And yes, I'm excited to engage with this group. So today I'll be talking about my research on bridging gaps between metrics and goals in modern machine learning systems. So these days, it goes without saying that machine learning is pretty deeply embedded into every sector of our public and private lives, from healthcare to social. Oops. Oh no, it went all the way to the end. Okay, that's weird. Let me just go back to this. Yes, from healthcare to social media, and now even large language models. So as these technologies are getting more and more sophisticated, there's both extreme excitement and there's also apprehension for, how do we study societal impacts in this new frontier? So to understand these societal impacts, I'm going to step back for a moment to the development of these systems, which often looks something like this, where you start with the development of the technical ML system, which includes formulating an objective that, developing some model architectures, collecting data, optimizing these objectives, and maybe some like pipeline engineering. And these systems then get evaluated with some performance metrics, which include things like maybe user interactions or offline accuracies, A/B testing, maybe even audit metrics. And if these metrics all kind of check out and look good, then the ML system is deployed, and from there we see the impact. So these performance metrics are really the gate that controls what gets deployed, but the problem is that they don't always tell us everything that we need to know about the eventual societal impacts, which means that the impact might not actually match the developer's goals. And it turns out that this potential mismatch between performance metrics and impact has been known for a pretty long time in many different fields. And some of you may be familiar with this concept of Goodhart's law or Campbell's law, and maybe this version of it by Marilyn Strathern, who is an anthropologist, might be familiar to you, where when a measure becomes a target, it ceases to be a good measure. And so this is colloquially used as Goodhart's law and said by Marilyn Strathern in 1997. And another quote that I find relevant from the same work by Strathern is describing a problem where aims are conflated with objectives, that is, with how one organizes oneself to achieve them. And I like this quote because it talks about objectives in a fairly general sense here. And here she's referring to accountability metrics that were initially used in educational institutions and then picked up by financial and business organizations. So these kinds of mismatches and ideas are all relevant to today's metric-driven machine learning system development, but also, I want to highlight these statements were published before modern internet search engines and social media were even really created. So in these modern uses of ML, my goal is to study the societal impacts of these systems, and in my mind, the key step to get there is to understand and bridge these gaps between metrics and goals here. And by metrics, I mean, what is the system being optimized to do? And by goals, I mean, what do we actually want the system to do? So today in this talk, I'll talk about 4 ways that I've approached these sorts of gaps between metrics and goals in my research so far. First, I'll talk about technical gaps between theory and practice that show up in fair machine learning, or fair ML, which is one piece of the puzzle for understanding societal impacts of ML. And this includes complications in solving fairness constraints when your data is noisy regarding the groups that you might actually want to protect. Next, I'll talk about some goals and impacts not covered by fair ML. And specifically, I'll introduce a technical notion of shape constraints that differs from statistical group-based fairness, which I'll discuss in the first part. And then third, further zooming out from the technical realm, I'll do a deep dive on further open problems in the gaps between metrics and goals through a qualitative study that we did on the uses of ML in education. And finally, I'll briefly touch on some of my most recent work, which is currently in progress, on the interactions between metrics and incentives. And by incentives, I mean like what incentives are induced in an ecosystem of actors and stakeholders that are interacting with a machine learning model. So this is probably most closely related to Goodhart's law in a strategic sense. So I'll start with technical gaps that show up in fair machine learning. And here I'll be talking about some joint work with Wang, Hari, Andy, Maya, and Mike. So giving some background on group-based fairness constraints, a simple example of a group-based fairness constraint is a statistical parity constraint, which says that the machine learning model should predict positive outcomes at the same rate across different groups. So for example, let's say a model is predicting college admissions. Statistical parity says that this model should predict admission at an equal rate across male and female applicants, let's say for this example. So in this case, yes, the green region shows the proportion of applicants that are admitted by the model. This is just one example of a possible fairness constraint. There are many other constraints like this that are based on prediction rates, like maybe looking at true positive rates or false positive rates. Those are also known as like equal opportunity or equal odds. I won't get too far into those today, but once such a fairness constraint is chosen, then it can be enforced by solving a constrained optimization problem of this form, where you're just minimizing some loss subject to some group-specific constraints. And we actually show how to do this in a lot more detail in this JMLR paper, but I won't get into too many of those details in this talk, because since in this talk, I'll focus on the fact that the ability to solve this problem is still contingent on us actually knowing the protected groups in the data. But in practice, data can be a lot more complicated. Specifically, I'll talk about this case where what if the data does not include true group labels G that we might want to have these fairness constraints for, but instead some proxy labels G hat. For example, one way this comes up is if the group labels in the data are overly coarse. For instance, in that statistical parity example, as I just described, I only had male and female group labels, but that would not include non-binary folks or intersectional groups. Oftentimes, the types of like group-specific or demographic data is not usually or may not be expressive enough, even if it's collecting things like race categories on the census. Another way that noisier proxy group labels can arise is through survey response bias. So if you have survey data, survey participants may actually be incentivized to obfuscate their responses regarding sensitive attributes for fear of disclosure or discrimination. So this data is from the Human Rights Campaign asking, performing an HR survey on people's comfort with disclosing their sexual orientation or gender identity. And while 72% of folks said yes, as many as almost 30% of people said either no or don't know or refuse to answer. And the problem when we're trying to enforce fairness constraints with this kind of, or audit or enforce different kinds of statistical fairness with this kind of data is that often those who wouldn't want to answer are those who are in the most vulnerable categories. So there are other ways that like noisy data or noisy protected group information can arise. Those are just a couple of examples. Data can be outdated, for instance, or you might have like even purposefully injected noise via differential privacy. But the question that I'm going to focus on now is mathematically, how do we solve for fairness constraints with respect to some true groups that one cares about G when we only have access to some noisy version of this G hat? So one straightforward way to do this would to just simply be, well, let's just substitute the labels G hat that I have. Let's just use what we have and solve the same optimization problem as before with that technique from that JMLR paper that I mentioned. So we could say, okay, I'm just going to sub in G hat here for my constraints. It turns out, though, that this doesn't usually work very well. And the more noisy G hat is compared to the true group G, the higher the constraint violations can end up being. So in our paper, we show how this happens both theoretically and experimentally, and I'll just give an experimental illustration of this here. This is just a simple experiment where we use the UCI adult census data set and we trained a model to predict whether someone has high income or not. And here we look at violations in an equality of opportunity fairness constraint across race groups. So this is like we're looking at gaps in true positive rates across race groups. And so to understand the effect of noisy labels, we artificially created these noisy proxy groups G hat by uniformly perturbing the race groups in the data at 5 different noise levels, 0.1 to 0.5, and then constrained for fairness with respect to this noisy proxy. So this plot shows the change in true group fairness violations as the amount of noise between the true groups and the proxy groups increases. So the black line at 0 indicates that fairness violations are 0. So the constraints are totally satisfied. We have like equal true positive rates across all the different groups. And we find that as the proxy group gets noisier, so the group noise level goes from 0.1 to 0.5, we get worse and worse at controlling the true group fairness violations. So the next question we ask is there an algorithmic way to do better than this naive approach? And the answer is yes, if we have more information. Specifically, we have to, let's assume that we have access to some main training data set, which contains the proxy groups or some noisy groups, the target labels, and then some inputs features X. And then we also have an auxiliary data set, which contains both the proxy groups and the true groups, but none of the other information. So all we need to know is just what is the noise model between my true groups G and my proxy groups G hat. So this kind of auxiliary data set can be easier to get because it doesn't actually contain maybe the true labels that we care about. So what we would do with both of these data sets is optimize for the worst case over the set of group assignments that are consistent with this information. So basically we can, like, one thing you can envision here is, let's say, let me like substitute in different realizations of G hat in the main training data set and try to like satisfy constraints for each of those different realizations. And as long as those constraints are satisfied for as long as one of those realizations matches the true groups G, and we satisfy the constraints with respect to that realization, then we will actually satisfy constraints with respect to the true groups G. So we're kind of looking at this like worst case robust type of approach. So what we find with that, I can maybe if we have time, I can go into the actual mathematical formulation of that, but in that same experiment as before, what we find is that this robust solution does actually manage to control the fairness constraint violations with respect to the true groups, and it does so much better than just that naive optimization method where you just like substitute in G hat for G. So yeah, like the goal here with these plots is to have the plotted fairness violations be below this black line at 0. And the robust method does actually manage to mostly do this. But this doesn't happen for free. The cost that we pay comes in terms of error rates. So the overall error rates for the robust method increase as the noise level increases. So this intuitively happens because as you add more and more noise, the robust method has to control for like wider and wider perturbations. And so the worst case gets like worse and worse. So in order to still make sure that like you satisfy the constraints, we now have to incur higher error. So there is no free lunch here, but the cool thing with this work is that methodologically, now it's possible to purchase this lunch at least with some error, like cost and error rates. Okay, so as a real world example of where this problem shows up, a couple years ago, a group of economists at the University of Pittsburgh, who I'd been talking to, they acquired this giant, rich, longitudinal credit report data set from Experian, and they wanted to analyze fairness in credit scoring in that data set. So specifically, they wanted to analyze racial inequity in access to credit over time. And unfortunately, though, this data set did not include any race labels, but it did include other correlated information like zip code and income. So the goal was to see whether some of those group fairness constraints could be measured and enforced in this setting and whether we could see how those affect actual different race groups. So with this example, I want to cast this back to at the beginning where I was this difference between metrics and goals that I was talking about. So for metrics, for like what is the system being optimized to do, we have that, well, credit scores are being optimized to predict default risk in this Experian data set. And in addition to this, this group, Albanese and Van Mossi, were adding these, we're trying to look at what happens when you add some statistical fairness with respect to some known quantities in the data, zip code and income. But stepping back to look at the broader goals in this setting, broader goals include, well, they're really interested in looking at fair allocation of credit for marginalized groups, as well as in credit scoring in general, there's this issue of wanting to not perpetuate inequality in life chances across social groups via these kinds of scoring goals. So there are clearly these goals are broader than like the metrics that we have. And specifically, the specific gap that we just addressed is the fact that zip code and income, which are contained in the data, don't actually match race groups that one might actually want to consider in practice. But as you can probably see with these broader goals, statistical fairness doesn't cover everything that would be of interest to economists and social scientists here. Okay, so actually, yeah, maybe I can stop for some. Are there any quick questions in this first part? Okay, maybe I'll go on and then we can always come back for more questions. Okay, so so now we've talked quite a bit. We've talked so far about group-based fairness and technical gaps that show up between theory and practice when we're trying to enforce these kinds of group-based fairness constraints. So in the second part of this talk, I'll zoom out from this sort of like group-based paradigms of fair ML to consider other impacts that statistical group-based fairness can also overlook. Specifically, I'll introduce this notion of shape constraints and compare and contrast these kinds of shape constraints with the statistical fairness constraints that we just talked about. And this is joint work with Maya Gupta. So to illustrate these shape constraints, let's consider an example using data from the Law School Admissions Council. And suppose that a model is trained to predict if a student will pass the bar exam based on their undergraduate GPA and LSAT score. And this is, of course, a very simplified model, but models of this form or structure have actually been used for graduate admissions in the US, and I'll go into a more detailed example of that later. So what we did here was, we just trained a neural network using these very simple two features and that single label of probability of passing the bar exam. And this plot shows how that model ended up behaving. So in this plot, the lighter areas show regions where the model predicts a high probability of passing the bar exam, and darker areas show low predicted probabilities of passing the bar exam. And kind of as expected, the regions with high undergraduate GPA and high LSAT score, in those regions, the model predicts high probability of passing. And then for regions where you have low undergraduate GPA and low LSAT score, the model predicts low probability of passing the bar exam. But what's interesting here, and where the problem comes from, is that there are actually many regions in between where increasing GPA can actually decrease the predicted passing rate, and similarly for increasing LSAT score. So what this means is that for these regions, actually if a student were to actually marginally increase their GPA, their predicted probability of passing would be worse. And one clue as to why this happens is that the training data is sparse where the model behaves badly. So this plot on the right shows the distribution over of the actual training data that we saw. And so where we might think this comes from is perhaps the model is overfitting to noise in these sparser regions of the data. But this kind of overfitting is super common, and it's a common problem that we don't always have control over. In fact, in most real applications, you almost never have like a uniform sampling over all parts of the feature space that you would care about during training. So in this particular example, the training data is kind of concentrated in the upper right because we have more data with higher GPA and higher LSAT scores. And part of that reason for that is because this data came from students who have already been through law school. So these are students who actually had the chance to take the bar exam and either passed or failed. And so that means that they would have been admitted at some point into law school. And so on average, probably have higher GPA and LSAT scores. But this kind of model would hypothetically, if it's actually being used to evaluate students applying to law school, it would be applied to a lot more students in the sparser regions with possibly lower undergraduate GPA and lower LSAT score. And so more of the actual students who would be like subject to this decision making might be in these parts of the space that behave badly. So how do we fix this? Well, it turns out that there is a way to make the model behave more reasonably without sacrificing accuracy using shape constraints. Specifically, we could add a monotonicity shape constraint, which is shown on this plot on the right, where these shape constraints say that all else equal, increasing GPA should not decrease the model's predicted passing rate. And we could also simultaneously enforce the same constraint on the LSAT scores. So now with these monotonicity constraints, a student won't be subject to kind of those strange regions of the model. So there's less ability for, there's also less ability for students to sort of game the system by like arbitrarily lowering their GPA. So overall impact on students, if this type of model were to be used in an admission system, would be better. So how does this relate to the statistical group-based fairness constraints from before? Well, the monotonicity shape constraint takes this form for a model function f, which basically says that higher GPA yields higher scores, all else equal. Previously, we talked about the statistical parity fairness constraint, and the monotonicity shape constraint can compare to a sort of one-side version of this statistical parity fairness constraint, which says that, okay, increasing some feature, or say here higher GPA, that should yield higher scores on average. So these differ conceptually from each other, and specifically in a theoretical sense, satisfying the statistical parity constraint actually doesn't imply anything about whether you would satisfy a monotonicity shape constraint. Like you could satisfy statistical parity, but still have arbitrarily like large violations in the monotonicity shape constraint. On the other hand, satisfying the monotonicity shape constraint actually does imply that you satisfy, or does imply a bound on the violations in the statistical parity fairness constraint. So there is some sort of relationship here that in some sense, the monotonicity shape constraint is a bit stronger. But of course, this also depends on the underlying distributions across the features. So for anyone interested in like giving these shape constraints a test run, because they're kind of different from the typical statistical parity fairness constraints, we have an open source library and code tutorial on TensorFlow. But also speaking of real world examples, predictive models like that law school admissions example have actually been built into actual admission systems today, and already, some of us may have been subject to these. So in 2013, UT Austin had trained one such model to aid in graduate admissions when the number of applicants to the CS department had been growing faster than their resources could handle. And the system that they came up with was the Graduate Admissions Evaluator, or GRADE for short. And what GRADE would do is take an applicant's admissions packet, including their resume, personal statements, transcripts, GPA, GRE scores, all that. And using that information, the machine learning model was trained to predict whether or not an applicant would be admitted by the admissions committee. And they had data for that in the form of past admissions decisions. So this system ran quietly until 2020, when public discourse led UT to actually pull that model. And in their tweet announcing this, they cite the potential to encode bias into ML systems and into ML-based systems like this GRADE model. So stepping back again and looking at the metrics and goals in this graduate admission system, the metric here would be that GRADE was optimized to accurately predict the probability of admission from past data. But clearly there was some like mismatch with goals here, given the discourse that ended up surrounding this and the fact that they ended up having to pull this model. So yeah, maybe Wumbo, this is a part where we could have some interaction from folks who are listening. So I'll ask the group here, like, does anyone have any other goals that you know of that would also be important to consider in this setting? Maybe you could, or I guess maybe folks can either unmute or like just type stuff into the chat. Since the exercise here is to just kind of compare what is the thing that we're training and what are the actual like ways that we want the thing to behave. Okay, I'm not really seeing interaction. Okay, that's okay. We can move on and then maybe talk more about this in the Q&A portion. So as far as what we actually want the system to do, some things cited in this paper were, well, they want to admit students who are likely to do well. So they want to make sure that the department ends up having high graduation rates or high retention rates, et cetera. But some other goals that came up in the discourse surrounding this system were things like, well, we want an admission system to consider life circumstances holistically and maybe promote diversity in the department and the field. So relating this to the technical piece that we just talked about regarding shape constraints and fairness constraints. Okay, in this section, the gap that we talked about was that, well, okay, high accuracy doesn't necessarily prevent or can't prevent unfair penalization with respect to maybe some attributes that should be rewarded or should correlate with whether a student will be likely to do well, such as like GPA or GRE scores or things like that. But again, like there are still more gaps to be addressed here, and shape constraints or even other kinds of fairness constraints may not address these other issues of wanting to consider life circumstances holistically or broader issues of diversity in the field. So this even broader set of goals brings us even further outside of the realm of what's technically defined as fair ML and the sorts of things that I talked about in the first and second parts here. So my next step in trying to understand these gaps better was to go and talk to actual domain experts. And so in this third part of this talk, I'll do a deep dive on gaps in problem formulation and interventions that through a qualitative study with expert interviews on ML for education. And this is joint work with Lydia Talani and Rediat. So beyond admissions, ML is also quite prevalent in education, not just in, like, we might think of massive open online courses at first, but not just in things like massive open online courses, but also in higher education and K-12, like sprinkled throughout these systems. So we talked about admissions, but machine learning is also used to predict student dropout risk. It gets used for automated grading and essay scoring, predicting test question difficulty when designing standardized tests. It gets used in intelligent tutoring systems, chatbots for advising, and with recent ChatGPT release and large language models, these uses are growing and growing for better or for worse. So we studied the societal impacts of these applications, of these various applications of ML in education through a qualitative study, and our methodology looked like this. So we started with by sampling 20 different papers from a survey on AI for social good that apply ML in different education settings, like the ones that I just described. And these were published in ML conferences like AAAI, KDD, and HCI. And we studied these papers through the lens of interviews with 15 different education researchers who were, say, faculty in graduate schools of education and different kinds of like research directors. And the data analysis with this kind of qualitative study is a pretty systematic thing in the social sciences, where you start with some interview transcript data, then we group themes from those transcripts and develop codes to group those themes together and understand them, until finally we discuss and iterate until we can distill these transcripts and interviews down to some findings that that can then be nicely packaged and presented. So the question that we focused on with this qualitative study was, are the paper's stated or implied goals, objectives, data, and success metrics actually aligned with the actual needs and goals in education? So pretty similar to the problem that I described at the beginning of, well, do the metrics actually match the goals? And what we found in order to like kind of structure these findings, what we found is there's a lot of issues that come up in these gaps that go kind of outside of just your typical technical supervised ML problem setting. So in order to understand and contextualize these issues, we actually had to reimagine the machine learning lifecycle. So to start here, the box in the center here is what I'll refer to as your typical ML problem box, which is what usually gets studied with these like fair ML kinds of settings, where you have some data sets with maybe some input features and a prediction target that's chosen. And from that data, a model function gets trained. And that model function produces some predictions, which then get eventually used to pass down the pipeline to make decisions in education. So I'll call this like the technical supervised ML scope. But what we found in these interviews with the education experts was that when we're looking at gaps between metrics and goals here, many of these gaps arise before you actually even get to the machine learning problem box. And first, there are some practitioners and researchers who have some education goals who first have to like formulate these into a machine learning problem in the first place. They have to choose what kind of data they're going to get, where to get it, and what kinds of predictions that they want to make. Second, once those predictions are actually made, there's another translation from those predictions to actual interventions that will ultimately impact the education stakeholders. And in this process, you also see some of the gaps happen between the metrics and the optimization problem and the actual impact. And of course, there's also a validation feedback loop between the two ends of this system. So what I'll do now is talk about a couple of main findings from these two parts. From these two types of gaps, and show how they relate to broader gaps between metrics and goals in machine learning systems. So first, I'll talk about the translation from education goals to actually formulate machine learning problems. So one common theme that came up throughout these interviews was that in these machine learning for education papers, simple short-term metrics are often used in place or as a proxy for broader long-term goals. These papers would often focus on a single quantitative metric, such as improving on-time graduation rates, where the actual education goal is broader and longer term. So, for instance, one of our interviewees said that, maybe we don't want to limit ourselves to just graduation rates. We're also looking at other things like retention rates and so forth. But something like a retention rate is harder to measure because it's a longer term goal. In addition to that, another participant mentions that graduating with satisfaction is something that they also care about beyond just like whether or not somebody graduates. But graduating with satisfaction is also harder to measure and use as a metric because this is a more qualitative notion that's harder to kind of distill into a single numerical metric. Another like interesting point that came up with this translation between education goals and an actual problem formulation in the machine learning setting is this issue that in education, there's often many stakeholders that have competing goals. And this figure is actually taken from this kind of classical figure from education research by Yuri Bronfenbrenner, which like kind of shows that for a given student, their learning is determined by many different actors in their environment, including, their family and their schools and their teachers, but also like broader systems of government agencies, social services, and things like that. So in all of these, in this like kind of bigger environment, there's many different actors here, which may all have their own different objectives and their own different, like, I guess, goals for the child's eventual education. For instance, like the government agency might care about employment ultimately, or economic benefits on the long run. Your more local communities might care more about the students learning in a more holistic way, or their more like personal development. So many different goals here, many different stakeholders. And this all kind of complicates the problem formulation process when you actually have to just come up with like a single machine learning component. Okay, so I talked about this kind of first part where we're translating problem formulation, or yeah, we're translating goals into this machine learning problem. Next, now I'm going to talk a bit about what happens when you actually have to translate from predictions to interventions. So in thinking about the translation from predictions to interventions, now I'm going to use an example where you have a machine learning model which is predicting the probability that a student doesn't graduate on time. So one issue is that showing these failure risk predictions to students can actually demotivate them and lead to a self-fulfilling prophecy. So if you were to actually just show a student that like, hey, this model is predicting that you're not likely to graduate on time, then this one participant says, well, it doesn't seem well connected to research about what's actually going to motivate people to do better. And another participant points out that there's also a tendency for these kinds of systems that are trying to like predict risk of not graduating to stigmatize students. These scores also affect the behavior of teachers and family and in the surrounding institutions as well, like we just described, these kinds of institutions that affect a student's performance, where a teacher might, upon seeing some scores, allocate more of their limited time to students that would be more likely to graduate. Since, if they have limited resources, they might want to, they're like, oh, if they see that a student is not likely to graduate anyway, maybe they will allocate fewer of their resources there. In a more like optimistic sense, I think some of the intentions behind these systems are to help teachers allocate more resources towards students that are at higher risk, but in practice, different reward structures might not actually lead to that happening. So how might we like overcome some of these gaps with interventions? Well, one thing that interview participants repeatedly pointed to was the value of building models that could provide actionable insights. So for instance, with these sorts of risk prediction models, instead of saying you're not going to succeed, an educator might care more about, well, let's talk about what are the decisions that one needs to make or pathway forward that will allow a student to succeed. And I want to note that here, when I say actionability, this is different from other like typical notions of interpretability in machine learning. And the educators that we talked to were less interested in interpretability in terms of feature importance. So a lot of the papers that we surveyed would often come with these kinds of like feature important graphs, which would say that like, let's say your model is predicting risk of dropout. They would be like, okay, here's the N most important features that the model identifies that correlate with whether a student will drop out. But the problem is that, well, these feature importance plots, like the top end features were often things like, well, what were your parents' income? Like, what was your parents' education level? Things like demographic information that a student couldn't actually control or action on at all. And so the educators that we talked to, or the education experts that we talked to, said things like, well, what's most interesting to them is not, I wonder if the demographic factors might matter more than the behavioral factors. To them, they care more about, well, what can you actually do to help kids get off the trajectory they're on if they're not on a good trajectory? So this is sort of this is a very much an open problem as far as like the technical machine learning world goes. And I don't think that there's currently very many like good solutions out there right now that can provide more actionable insights rather than just these sorts of like feature importance plots. So in summary, from this qualitative section, we've talked about two different translation gaps that can show up when looking at the gaps between metrics and goals. First is this translation gap between education goals and the actual machine learning problem via problem formulation. And the second is this translation gap between predictions and interventions. And so casting this back into where we were talking about metrics and goals at the beginning, let's consider this third real world example of early warning systems, where in an early warning system, you have some machine learning model that's trained to accurately predict a student's risk of not graduating on time. And these systems are out there now. In fact, like millions of dollars were spent on building a system like this in Wisconsin public schools. So here, the model is trained to accurately predict risk of not graduating on time. But from the framework that we just described, we can identify several gaps between that and the goals. So the broader goal here might be, well, okay, we want these early warning systems to help teachers identify and help at-risk students. We might also, overall, the goal with those investing money into these kinds of systems they're trying to overall improve student learning and student outcomes, especially for those who are at the most risk. But our previous framework of looking at problem formulation and interventions helps us identify several gaps here between this metric and what the system's being optimized to do and what we want the system to do. For instance, graduation isn't the only important student outcome, as we first discussed earlier. There's like retention rates and whether they graduate with satisfaction. Showing predictions to students can also demotivate them. So this is a sort of gap between like, okay, how are you actually using these risk predictions? And then they're also like risk predictions don't help teachers take action. So if you want, if we want a technical system to actually achieve some of these goals, we may need to think kind of outside the box or expand our technical design scope to be able to think about what are some like actionable recommendations that we can make. Okay, so those gaps that I just discussed, and these last gaps in like problem formulation and interventions, these are unsolved gaps, and bridging them is very much an open problem. Whereas in the first two parts of this talk, on bridging these technical gaps and those like shape constraints, those are more technical solutions that exist for like kind of within that machine learning problem box. So in this fourth section, now in this last part, before we go to Q&A, I want to give a preview of some ongoing work that starts to address some of these unsolved gaps that arise when machine learning interacts with an ecosystem of agents and affects their incentives and behavior. As we saw in like the education case, we have these sorts of ecosystems where many parties are interacting with each other and affecting the final outcome of the students. So specifically, I'll talk about one problem that I'm trying to understand right now, which is whether looking at causality and the changes in outcomes can lead to better total welfare than just optimizing for outcomes. And the best illustration of this, or one like very clear illustration of this for me, comes from the use of report cards in healthcare. So I'm going to jump over to the healthcare application for a second. So in 1994, the New York Health Department started collecting and publishing these healthcare report cards, which basically reported surgery mortality rates for some like high-risk cardiac surgeries for different hospitals and different surgeons. And then they would like rank these hospitals and surgeons in order of their, you could then rank them in order of their mortality rates. And this kind of came in the early 90s. This was kind of a time when accountability was a big thing in becoming very popular, at least in healthcare and in education, where there was a lot of these kinds of report cards coming out and these sorts of like data-driven peeks into how these systems are working. So unfortunately, like this study by Dranov et al. In 2003, and it showed that actually like these healthcare report cards didn't actually always end up improving patient welfare. And specifically, with the report card that was looking at mortality rates for this cardiac surgery, due to this ended up leading to selection behavior on parts of the hospital and on parts of the patients, where the hospital could now, like by selectively treating healthier patients, actually they could improve their mortality rates, but this meant that they were actually not helping more severely ill patients who might have benefited more from treatment. So the more severely ill patients actually ended up experiencing worsened health outcomes after these healthcare report cards were introduced. In the modern day, these types of outcome-based healthcare report cards are still very much prevalent and being used. Specifically, and yeah, there's like also quite a bit of investment being put into these areas where like most of today's healthcare reporting comes from at least in the US, comes from the Centers for Medicare and Medicaid Services, or CMS, which over the last 10 years spent $1.3 billion on these kinds of development of quality measures. And there's also quite a bit of investment on part of the physicians and the hospitals as well, where in 2014, these practices spent 15 hours a week just working on trying to report these quality measures at these very high annual costs. And the way that these eventually percolate down to like actual patients in the modern day is through agencies like the US News and World Report, which reports this like best hospitals honor roll. We also have that like, I'm from California. In California, there's a California Patient Safety Honor Roll, which like kind of puts together and collects a lot of these sorts of CMS metrics. Oops. Okay. And then on part of the doctors, you also have this like Medicare and Medicaid also has this direct merit-based incentive payment system, which like directly compensates doctors for how well they do in these kinds of metrics. So they weight, the compensation comes from things like quality metrics, cost metrics, improvement activities. And these quality metrics are very actually structurally similar to that first New York Health Department mortality rate metric that I just described. And if the doctor's final score in these metrics is above some performance threshold, then they receive a positive adjustment to their payments. And if it's below the threshold, they actually receive this sort of penalty and negative adjustment to payments. So there's like a clear like line of incentives here. So connecting this to this like broader issue of whether these metrics actually meet goals, with these healthcare report cards, the metrics here, or what the system is being optimized to do is, well, currently we have a metric which is ranking hospitals and doctors by, say, surgery mortality rates, or just by outcomes over treated folks. And the goals here are to improve patient safety and welfare by increasing accountability. There's this like adage that sunlight is the best disinfectant. So the goal here is like, if by measuring these institutions, we can improve their practices and behavior, then that would be ideal. These ranking systems are also trying to like help patients select providers that work well for them and overall incentivize hospital improvement. But these gaps that I'm currently working on addressing in this kind of incentive structure is that, well, one gap is that we just described is that hospitals can selectively treat healthier patients. And so if that's the case, then like ranking by just an outcome measure would not lead to like the kinds of these goals that we have for improving patient safety and welfare. Second, another place where a gap could arise here is that hospitals or doctors may have more patient information than regulators who are trying to audit these systems and measure these, introduce these kinds of accountability metrics. So these two gaps and these kinds of incentive gaps are a subject that I'm currently working on, and is like some I don't think I have much more time to like go into that, but this is ongoing work. So okay, so wrapping up this final section, overall I see this interaction between metrics and incentives in an ecosystem of actors and stakeholders to be an important path forward in understanding the societal impacts of machine learning, especially after having worked in depth on some of these technical implementation gaps in these like first and second parts. And then also working to enumerate and understand the limitations in our technical design scopes, as we described in the third part. So if there's one broader takeaway from this talk, it is that while machine learning is now very, very good at optimizing numerical metrics, there's a lot more work to be done in figuring out what we want to optimize and what it means to optimize these metrics for society as a whole. Okay, many thanks to all of the many folks that I collaborated with here. And please feel free to ask any questions now or reach out to me by email afterwards.
Okay, thanks for Serena's talk. So let's move to the second part, which is our Q&A session. So today we have Zhimeng as our discussant. So shall we start with Zhimeng first?
Okay. So thank you for sharing your research. Actually, I have some research experience on fair machine learning. So I really learn a lot from the discussion of the metrics and the goals. So I have questions. The first question, are the metrics enough to show the model is fair or not? So for example, if I can achieve a quite low score on the statistical parity, can we just say our model is fair? And the second question is that I want to know the relationship between different goals. So if my model can achieve fairness with respect to race, will this affect my fairness performance with respect to another feature, maybe age? I want to know if it is possible to achieve fairness with respect to all the goals. So that's my question.
Yeah, great questions. Okay, so for your first question on, okay, if you satisfy statistical parity, does that mean that your model is now fair? There's a couple, okay, like, I think the first thing to like step back and ask in that setting is, well, what are the actual like broader societal impacts of this model? Like, do you, let's say we're in like back in the admissions setting where you have statistical parity across say gender groups in your college admissions model. We might, if we want, I think what I'm trying to argue here is that like, when we consider whether or not that model is fair, it's really more important to consider like, what are the broader like impacts that I want in the system? Not just like, is my specific admissions decision like allocating the same number of admissions proportionally across like applicants, but more like, okay, if I care about like what is the purpose of even like putting that constraint in the first place? Is it to try to like promote diversity in the student body and in the department, in which case like is, you know, it could be that statistical parity is the right thing, or it could be that like yeah, it could be that you might have to look at a more like, okay, compositionally with this student body, like I want to make sure that you have enough representation from each group, let's say. So yeah, so I think my answer to like, is statistical parity fair is more like, well, it depends on the application, and we should think about like, what are the impacts that you actually want to achieve, and what's like kind of the long-term goal here. For your second question of like, okay, can you, if you say have statistical parity with respect to gender, like does that affect those fairness violations with respect to like other traits? I think that actually, from a technical standpoint, the first work on like the robust optimization stuff actually has like, I have actually some bounds in that paper that relate these things, where if you have like, say, correlation between gender and some other factor that you might care about, let's say like, okay, I don't know if gender is a great example, but maybe you have like age and income, for instance, as two different features that you're like putting constraints on, then like those might be correlated, in which case like constraints on age might actually lead to you having some control over constraints on income. As far as like what that means for broader like societal implications, again, this is like, we'd have to step back and see, well, okay, what are like the goals regarding how the system's being applied.
Yeah, thank you.
Yeah, thank you. Thanks for those questions. Great questions.
Is anyone else has any questions? Professor Sham, do you have questions? I see you showed hands at the beginning.
Yeah, that was just to welcome Serena. Thank you for a wonderful talk. I think it has a lot of implementations, especially in education. So when you present this to potential stakeholders who might use this for designing interventions, how do you frame the feature importance, and how do you convey the convey the best way to accomplish an intervention without further exacerbating the fairness and further exacerbating the bias, underlying biases that the data might embed?
Yeah, that's a good question. So, right, so you're saying, like, say we're presenting some
from your interview study with the event for education scenario, maybe you could use that as an example, perhaps.
right.
Like, what might be some insights that you got from speaking to those experts?
So as an example, like, let's say if you have some model that's trained to predict like dropout risk for students,
Exactly. Yeah.
you're saying like, okay, how can we have that model, maybe show those risk scores to teachers, but then we don't want to exacerbate like existing.
Right. And I think, like you alluded to, some people, it might be there could be a proxy variable for background, race, all kinds of things that we don't know.
Right.
So how might we overcome that?
Yeah. That's a very good question. So, yeah, so there, like, the thing that I would ask, the question I think we would want to focus on there is like, how is the teacher actually going to use this risk score? So is I think, yeah, like one of the things that came up in the interviews was like, it kind of depends on first how the risk score is being presented and like how it's being used. So if the risk score is like something where the teacher is trying to use this to identify people, like more at-risk students who they will like then allocate more resources to, then you would want like the model to do a better job of identifying people who like are more likely to drop out. So there you might be more concerned about making sure that like true positive rates are high, but you would be, and maybe true positive rates are like equal across different groups, or high enough for like groups that are particularly vulnerable. On the other hand, like if this risk score is being used by the teacher to say like, be like, oh, these students are probably like, I want to allocate resources to students who like would be more likely to like graduate and use those resources well, or who knows, or make the teacher look better. Then in that case, we might be more concerned about making sure that false positive rates are controlled for different groups, right? Because then you don't want to like over-identify students who might not otherwise. Basically what I'm saying is like, it depends on the way that the first question we have to ask is, how are the scores going to be used? And then second, like, what does that mean for where our different statistical errors fall? And how do those actually end up impacting people?
Thank you. Yeah.
I'm not sure if that, like, I think your question was deeper than that. So
yeah, I mean, I think it was more to do also, I mean, I think, that's a fine answer, but I also was thinking if there's a way to ensure that, because they may not always be transparent about how it's used. Sometimes it might actually stigmatize certain pockets of the student population, for example.
Right. Even,
having interventions to help retain some students might end up stigmatizing those students, right? Like putting them in some kind of remedial type training. And so that's what I'm worried about.
I think that's a great point. And that kind of thing actually did come up as well, as like, who's using these, like, are these scores being used by just the teachers, or are they also being used by the schools to try to allocate, like put students in places that kind of like benefit how good the school looks, like on a maybe public funding level? So there's like, more to this this picture here, which kind of like, this is part of what motivates this last part of what I'm working on now, which is like beyond just the specific container of like, here's the prediction model and here's like the one person who's using it. There's this like bigger social structure of incentives around like, who's deciding to deploy this model. What are people trying to like get out of trying to predict, say, like dropout risks for students? Where is like that, where are these like broader incentives pushing these different actors and stakeholders?
I thank you for saying that. When you had that exercise and nobody answered the question, the one reason that I couldn't think of the answer was that I didn't know who we are. What do we want? Are we trying to keep out the kids who will fail? Are we trying to help the kids who will fail?
Yeah, that's a great point, and I think that's exactly like, so I was, yes, we is super ambiguous there, and that's like
and if you don't mind me saying so, that's probably going to be even worse in a for-profit corporation.
Absolutely. Yeah. Right.
It's kind of like teaching to the exam, like some externally you might want to look good, and therefore you might kind of teach to the metrics, right? Or similarly, in this case too, you want to show numbers that make you look good, but that doesn't necessarily mean ethical use of your data or of your outcomes.
Right. Yeah. Yeah. And so I see all of these like little like sorts of technical fairness interventions and stuff. Like these are all kind of just smaller cogs in this bigger machine, at least in like how I'm viewing this system, where they may be useful in kind of mitigating some of these issues at like kind of a micro level, where we can say, oh yeah, I can kind of put a control on how true positive rates and false positive rates are interacting or are comparing across different groups, like for a particular model. But like in this like bigger system, there's like larger forces at play here that that I think may have more impact on fairness than like these specific technical fairness interventions.
Okay, does anyone has any questions? I think no. Okay, thanks again for Serena's talk, and it's also the end time for Young Achiever Seminar this semester. So thanks for everyone's attendance. So bye-bye.
Thank you, Benbo, for organizing it.
Thank you, Professor. Okay, bye-bye, everyone.
Bye.
Yeah, thank you, everyone. Thank you all.
Yeah, nice to see you. Bye.